Hello everyone, today continue from previous video. I will talk about doping and diffusion. So let's begin. First, I will talk about trends in doping process. In doping process, the shallow junction is very important because we should prevent VT reduction. And VT reduction it causes VT roll-off, and what parameters can affect VT roll-off? The one thing is oxide thickness. Oxide thickness is TOX, and the oxide thickness is shallow, more shallow than oxide capacitance is bigger because if the oxide thickness is small, gate field is well coupled to channel, so oxide capacitance will be really bigger. So and if we want gate coupling, we should COX will increase and CEFF, this means effective capacitance, this will be decreased. And next parameter is XJ. This means source. This is junction steps of source and drain, and this XJ will, if the XJ is shallow, then the VT will roll off more, because if the junction depth is more, the depth thickness is more bigger, and the depletions region will be more can go more from channel interface of oxide gate. So the coupling of gate will be not appear inside of body, so the charge sharing will be increased. So this is a graph of VT, delta VT and TOX, and this delta VT and XJ. This is like linear graph. And in the case of source and drain, we should keep the concentration that it has heavily doped, because we should reduce surge resistance. So when the device is smaller, then the resistance will be bigger. The resistor of contact regions is bigger than the resistance that is located in channel. So that is region. So when we dope much, so depletion will be decreased. So next we will talk about ion implantation. it is we should throw the ions in that electrically. So we make dopants to plasma, and we take electric field hard. So the dopants will go the vapor. So that is ion implantation. It is expensive, and it can be damaged in silicon surface, and amortization and shadowing and surface etching. This is the bad prospects, and this is a good thing. Where we can control the dopant steps profile and approximately, and we can process this in low temperature, and those uniformity will we can take big dose uniformity. And next, ion implanter. This is like this. Can you see this picture? First, in ion implantation, first ion source. This is ion and mass spectrometer. This is it took away specific ions selectively. And next, high voltage high voltage accelerator. It accelerates ions electively, and scanning system it makes more, it scans that, and it makes more uniform. And target chamber, it means wafer stage. First, ion source. How we make ions? That we make it of gas like BF3, B2A6 like this to this ion. So if we want to make ions, we should take energy. So how we can to take energy to this gas? First, ion beam generated by filament in use tungsten filament, and if we take energy, then the filament will hit, and the electrons will go out. So this means summer emission. So these electrons go to gas. These electrons hit electrons of gas molecule, so it transfers energy. And next, ion beam generated by plasma, it uses plasma, so that's it. And next, mass spectrometer. I talked about this. It takes away specific ion selectively. And this is formula. This is B is magnetic field, and if the ion is heavy, then the ions cannot go these selective ions because it is heavy, so the graph is more than like this, so it cannot go out. So if we control mass and magnetic field, if we can make select we can make this to selectively. Next is scanning system like this. And first we'll talk about electrostatic scanning. This means if we took electric field by vertical and horizontal, so if we this means it scans the target vapor that we want to doping. And next, mechanical scanning is mechanical scanning to vapor stage, and we use case both over and for uniform doping. And next, dose control. It means how much it dopes, and we use Faraday cup. And if we make hole the specific regions to regions we want doping, and the electrons, the ions goes on below. And if we measures the psi of ions, we can measure charge like this. So area dose is Faraday cups area Q. So we can talk this like this. And we'll talk about ion, implanted ion. First state is random collisions, and if the ions comes that it hit to lattice that located in substrate, so it means random collision. And this is backscattering. If we collision to lattice, if those make collisions to lattice, it can be like this, go out like here, go back like here. That is backscattering. And channeling is this is not those do not hit the internal lattice and goes to the between lattice, that is channeling. And we'll talk about stopping mechanism. Stopping mechanism is the mechanisms that the dopants, if the dopants took and it stops in a specific location. So first, nuclear stopping, and it means dopants goes and it make collisions to collision with nuclear of silicon lattice, and it makes dramatic scattering, but it can make very big damage. So and next we will talk about electronic stopping. And if the positive ions move, the velocity will be slow because this electric field will make like this, so the velocity is slower. So this energy transfer will be decreased, but it can be the lower lattice damage. So it makes the electronic stopping. First, the electronic stopping will appear, and next the nuclear stopping will appear. So this is the first electronic stopping, and the electronic stopping will be appear, and nuclear stopping will finally the nuclear stopping will appear. And if the electron and if the energy is low and heavy ion, we use nuclear stopping. And if the energy is high and it has light ion, we use electronic stopping. And this is selective implementation. If the concentration of interior dopant will be smaller than background doping concentration, that means we make good masking. We make good mask, and most over we talk about this 10-1. This is the interior dopant concentration will be 1 and the background doping concentration will be 10. So that's it, and we'll talk about junction depths. And junction depth, it means like we can talk this formula, and it means where the mean project range is. Where is the mean project range, or what is it, the two concentration of that. So if we talk about the number, if we do background doping, the imperative dopant number and the point of imperative dopants this MB. This means background doping concentration. This point is junction depth. So this is graph, and we'll talk about channeling. And I talk about this. It not collisions with lattice because there is a hole, like hole. There is no lattice. So if we prevent channeling, tilt angle is given during ion implantation. So if we do ion implantation, we should tilting wafers, and we can make more collisions of dopants. But if we do tilting much, it can appear shadow effect, so we should not tilting very much. So in semiconductor process, to prevent shadow effect, we tilting of 7 angle. And we'll talk about lattice damage. If the ion is heavier, the damage is bigger. And we'll talk about advanced doping. And PLAD is plasma doping. It uses plasma, and it is called conformal doping, and it's used in FinFET and GAA because it can make much shadow effect. And RDF, random dopant fluctuation, and this means issue of the dopes randomly. This is the issue. And next we'll talk about thin diffusion. And the thin diffusion, it means if it has smaller than 100 nanometers thickness, that if of diffusion, and it has a diffusion. And there is two things in thin film diffusion. First, chemical vapor diffusion, and next, physical vapor diffusion. First, we'll talk about growth modes. First, 2D layer by layer growth. It means like this. Film and film, like uniformly put on this film, like this. And for example, as silicon and silicon. And next, 3D island growth. It means it grows like island because it hates this substrate, so it grows like this. For example, metals on silicon dioxide, and next mixed growth, and it means the mixed of like this and this, and if the growth grows continually, and and it makes island in specific time. And we'll talk about film crystallinity. And epitaxy means single crystalline atoms, and it has no grain boundaries and film quality. It has good film quality, but it is slow and it requires high temperature. And next, amorphous. It is it means it doesn't have a crystalline structure, so no crystalline structure, and in use island or mixed growth. Next, polycrystalline. It it means many of crystalline, lots of grain boundaries, in use island or mixed growth. And if the grain size is bigger, then the material mobility is bigger. Next, we'll talk about step coverage. This is very important. And this is a conformer, and this is a non-conformer steps, and this in case of conformer, it can make lift up, but this is a good for a lift up process, and but bad for metallization or cap filling. And if it has high aspect ratio, we cannot put this conformally. So step coverage is it means the ratio of film thickness below and up above this. So this picture, it is step coverage. This is film thickness here and here, and this is a ratio. This is step coverage. And next we'll talk about CVD. I talk about CVD is in-use chemical. First, the source gas goes on substrate, and the chemical reaction will be appear, and the gas products goes out. It means byproduct. And first in CVD, first APCVD it is process of 1 ATM, and it is simple system and cheap and fast reactions, and it has low step coverage, and it can make big pollution. And next we'll talk about PCVD. It is a process of using plasma, and it has low temperature and good step coverage, but it is expensive. And next, LPCVD, it is a process that's using in a very low pressure, and the mean free pass is there is a loss of mean free pass, so we can make big step coverage and uniformity, and there is a very low pollution, but it has high temperature and slow process. And else PCBD is good, can make good step coverage. And next, talk about reactor heating. There is a cold door and hot door, and it used to prevent chemical reaction on chamber surface. And next, ALD, and ALD means atomic layer depositions. And we can put anything that it has a precursor. First, we put precursors in vapor space, and the atomic components comes to vapor stage, and the chemical reaction will appear, and the purge will appears in here. It means it kills the different things. It means, and next, the second atomic components comes to here, and it is a cyclic process. So we can control thickness by how many we do this cycle. So this is the end of my video.